everybody. I'm Valentina and I'm presenting this work carried out with my colleagues Khurshid Aliev, Paolo Piantanida, Giulia, Bruno, and Dario Antonelli from Politecnico di Torino about automated anomaly monitoring and detection system for a Fan Coil Unit system. In this paper, we proposed an automated fault detection and diagnostic called AFDD systems that assist facility managers in informing operators to perform scheduled maintenance and visualizing facility anomalies on building information models. Since the paper is a part of a big project, the steps followed to develop this methodology is as following. So the aim was to represent maintenance activities for building processes by using this automated fault detection and diagnostic formalism. Steps of this work go through analysis of factors involved in the process of maintenance, analysis of activities, and analysis of maintenance processes. This paper goes deeper in the fourth step, analysis of data and information involved, and the outcome of this work is an AFDD model for a Fan Coil Unit system. This diagram contains all the information required for the maintenance management of a Fan Coil Unit. They are grouped according to the type of data collected, and this diagram is the basis for the data and information analysis phase. In particular, we have a series of general data linked to the technical data and data related to the environment in which the fan coil is located. In blue are the data collected through the sensors, as I will illustrate shortly, and in yellow are all the maintenance data linked, of course, to the technical data and general data. So the maintenance data must satisfy the technical data, depend on the data collected by the sensors, and are linked to the conditions of the location where the fan coil is located. This diagram proposed an example of the fault detection and diagnostics model for the fan coil unit maintenance. The presence of the fault is monitored through a set of sensors that must be installed on the fan coil unit. In particular, we have 5 sensors for temperature, 3 for voltage, and 3 for current. The faults which can occur in the fan coil system are insufficient airflow, motor bearing wear, capacitor failure, and insufficient water flow. For each of these faults, a corresponding action has to be taken: a clean filter, for example, in battery, change beers, replace capacitor, and clean filter and battery, and check a valve adjustment, for example. So then the maintenance process could be controlled real time, and when a fault occurred, the system informed the operator or other technician who are responsible to make the maintenance. By the experimental case study carried out on a fan coil in our department laboratory, the framework is demonstrated. As a building facility, we use the fan coil unit and all the sensors, temperature, voltage, and current sensor are installed on the motor and on other parts of the fan coil unit, and the building facility is connected to the BIM model. So all data that is coming from the fan coil wirelessly will be sent to the BIM model and plus to the data server PostgreSQL using the Node-RED. Here in detail, the list of sensors mounted on the fan coil unit, and the figure shows the motor of the fan coil unit with the temperature sensors and the battery with the sensor, and plus current and voltage sensors that are installed in some parts inside. Temperature sensor T1, T2, and T4 on the FCU monitor the temperature of the lever and return pipes, as well as the air intake and condition temperature, which should be between 0 and 90 Celsius degree. T3 is in charge of monitoring the air temperature in the 0-50 Celsius degree range, whereas T5 is attached to the motor casing and measured in the 0 to 100 range. The figure shows voltage, current, and temperature sensor attached to the FCU unit. According to this automated fault detection and diagnostic methodology, alarming system implemented to monitor FCU motor impeller monitors the motor voltage between 0 and 200. For this reason, the motor voltage must be checked more often, and the sensor board must send average readings to the server every time when the FCU is started or changed the speed. On the proposed anomaly detection system, electric power must be monitored in the first 10 seconds when the voltage exceeds the 200 volt. To illustrate the system's reliability, the following experiments were carried out. Sorry, I don't know why my computer do it by myself. Okay. The first was to gather balanced normal condition data from the FC motor, and the second was to create an unbalanced scenario by attaching 15 grams of mass to one of the FC motor's blades. The experiment was repeated 3 times, each at a different speed. In this slide, we can show the results of the balanced and unbalanced real power data are demonstrated. With the red line, we can see the unbalanced condition. We can see 3 peaks that they must raise the unbalanced condition, as illustrated in this figure. When an unbalanced condition occurs, the motor consumes a large amount of power, demonstrating the unbalanced condition that provides a threshold between balanced and unbalanced scenarios. According to the proposed monitoring algorithm, if the real power is within the threshold, the motor impellers is balanced. Otherwise, the motor is unbalanced. For the proposed algorithm, 10 seconds is enough to check the impeller because high power consumption occurs when the impeller starts to rotate, as explained in this figure. Data acquired from the experiment used to demonstrate balanced and unbalanced condition of the Fan Coil Unit motor impeller. These slides illustrate the Fan Coil Unit impeller balancing unbalanced condition. The difference between unbalanced current, IUB, and balanced current, IB, identifies the threshold where occurs unbalanced conditions. So in this case, the threshold is 2.4 for the balanced condition. If the threshold is more than 2.4, there is anomaly. To demonstrate detect the unbalanced condition, it is enough to observe the first 10 seconds when the motor rotation is occurred. Since the data acquisition sampling frequency is 2 Hertz, so the first 10 seconds are 20 sampling. Data of balanced and unbalanced conditions are enough to demonstrate those graphs. That in this graph we can detect unbalanced condition of the motor's impeller, and they are marked with the red notes, the 3 red dots. This anomaly is demonstrated also on the full data sampling from all the experiments. And finally, the Fan Coil Unit condition results and sensor data are uploaded to the BIM model using Autodesk Navisworks software by creating the PostgreSQL database using data tools settings. Following detecting anomalies on the Fan Coil Unit, the system visualized detected anomalies and sensor data on the BIM model, as shown in this figure. This data, as you can see, when here, when there is a delta more than 2.4, there is anomaly, and the fan coil on the beam model becomes red. That means that there is anomaly and operators must do some actions. So that means that require some maintenance. Other way, normally they are gray. This study describes an automated anomaly monitoring and detection methods for a single fan coil unit maintenance using IoT technology. The proposed fault detection method was implemented on the application layer and sends alarms to end users or managers when any anomaly happens in order for it to be efficiently repaired. BIM was used to visualize the monitored fan coil unit condition. An experimental case study was used to assess the reliability and applicability of this framework. And the introduction of the anomaly monitoring system into the BIM model would decrease the building maintenance plan by assisting facility managers in inspecting the monitored buildings environment. So, as a result, facility managers may benefit from the proposed methodology to handle maintenance issues. Facility managers may plan and schedule maintenance work in advance by using anomaly or failure signals from building facilities. Conditional and real-time data from sensors allows for more accurate maintenance, and IoT sensors data for building components within the BIM model makes maintenance work more convenient, of course. For example, finding the location of the failure component in the real-time BIM model would be simple. So thank you very much for your attention. If you need further information, here we have our contact, and we will be happy to answer and collaborate to other group about this research. Thank you so much.